Linear programming is a technique to maximize or minimize a linear function. So if you're trying to maximize profit or minimize cost. So this is a technique that we're going to go through, and it uses inequalities. When you hear the word objective function, an objective function has at least two variables, and it's what you want to maximize or minimize. So for example, it could be a cost, profit, utility, or yields. Constraints are inequalities that are also, I've also seen them called restraints or restriction inequalities. So it's some type of limitation that you have. So for example, you need to use at least 18 yards of fabric, or you need to use more than 20 hamburgers and hot dogs. So you have to look for keywords like at least, more than, no more than. And then the feasible region is the solution area of the system of inequalities. So the constraints are going to be all of your inequalities, and the feasible region is going to be where they come together. So the steps, I would write this down as, the first thing you want to do is figure out what your variables are going to be. So we're having two variables. The second thing you're going to do is you're going to write the constraints, or look at the restrictions in the words. And then also, a lot of times you're going to have the simple constraints of x is greater than or equal to 0 and y is greater than or equal to 0, because you're not going to want to have negative apples or negative cost or negative yards of fabric. Then you're going to graph inequalities and write the coordinates of the vertices of the feasible region. So if your graphs looks like this, your inequality, the feasible region would be right here, or the vertices of the feasible region would be right here, because this is where black and red meet, so these are the vertices. So then you're going to write the objective function. The objective function is usually a profit that you want to have or the cost that you want to minimize. Then you're going to plug in vertices, these are the vertices, into your objective function and figure out which vertex maximizes or minimizes it based on the context of the problem. So those were a ton of directions, but I'm going to keep going back through them as I go through this example. So a calculator company produces a scientific calculator and a graphing calculator. Long-term projections indicate an expected demand of at least 100 scientific and 80 graphing calculators each day. Because of limitations on production capacity, no more than 200 scientific and 170 graphing calculators can be made daily. To satisfy a shipping contract, a total of at least 200 calculators must be shipped each day. So in other words, there's a limit of how many graphing calculators and scientific calculators that we make. However, we need to make sure that we have at least 200 calculators a day. If each scientific calculator sold results in a $2 loss, but each graphing calculator produces a $5 profit, how many of each type should be made daily to maximize net profits? So we just don't want to bust out and make 500 calculators a day if we're not going to use them because they cost money to make. So what we're going to do first is, if I go back to the directions, I need to define the variables. So I kind of look at the end where it says how many of each type should be made. So the type, we're talking about graphing calculators and scientific calculators. Part 2, write linear inequality constraints based on variables. So our variables are going to be G and S. So I'm looking at, we need an expected demand of at least 100 scientific calculators. So scientific calculators has to be at least 100. Graphing calculators has to be at least 100. 80. And then we also have another limitation. Because of limitations on production capacity, no more than 200 scientific and 170 graphing calculators can be made each day. So we have to make less than or equal to 170 or 200 scientific and less than or equal to 170. But we know that we need to have a combination of at least 200. So I know that scientific plus graphing has to be at least 200. So this information down here is our objective function. This is what we're going to try to maximize. So I'm going to go to step 3, which is graph inequalities and write the coordinates of the feasible region. Okay, so I started making this scale, and now I'm just annoyed with myself that I made a scale that I didn't go longer this way. So it's going to get kind of messy, but I'm going to change this scale on the bottom. So I'm going to make this be 25. I want to go up by 25s. This is going to be 50. This is going to be 75. This is going to be 100. 125. This is 150. This would be 175, and this is 200. So I did that because over here it's scientific calculators less than or equal to 200, so I knew I wanted to get 200 on the scale. Sorry that it's messy. So, and it doesn't matter if I put scientific calculators or graphing calculators on the X or the Y in this case. So, and then my graphing calculators I'm going to have go up by 20. So this is 20, this would be 40. This is 80, 100, so I just don't have as much going up here. Okay, so I still don't fit 200, but it's better than what I had going on over here in the black. So now what I'm going to do is I'm going to graph all of these inequalities, and together the solutions of this will be my feasible region. And I'm going to collect the vertices of the feasible region. So because there's so many inequalities going on, I'm not going to shade everywhere that needs to be until the end. So this is S has to be greater than or equal to, or less than or equal to 200. And this has to be S is greater than or equal to 100, right here. So I know that so far in between here and here is going to be shaded, but I'm not going to shade it all the way yet. And I know that graphing calculators have to be greater or equal to an 80 and less than or equal to 170. And the last one I know is, so I know these two, so far we have this box going on. And the last one is scientific plus graphing calculators, have to be at least 200. So I'm going to do this by graphing intercepts. So if I cancel out the S, the G is 200, so I put a dot at 200. And then I can also do the same thing for S or G, cancel out the G, and the S is 200, so right here. Oof, didn't connect that very well. So when at the end it's greater than or equal to 200, so this part would be shaded. All of this, so where all of this overlaps is this shape right here. So these are called the vertices of the feasible region. So I need to figure out what G and S are for each of these vertices. So let's stick with the ones that are simple first, and then I make a chart here. So I'll make a chart of the S and of the G. And so one of the solutions right here is 200 and 170. So S is 200, G is 170. That's this vertex right here. This vertex is 100 and 170. So S is 100, G is 170. This vertex right here is 170, 80. Or I'm sorry, 280. Now I did the 3 easy ones. So what you need to do, I'll change color, is these ones that are kind of on the diagonal and my scale's not so hot and my graphing paper is not so hot to show what this true intersection is. So this intersection right here is where this line intersects this line. So look where this line intersects this line. So basically you're solving the system of this S equal 100, because that's the vertical line, where it intersects S plus G equals 200. So you're solving that system of equations. So you can solve it a couple different ways. I'm just going to use substitution. And then so S is 100 and G is 200, or 100. Then the second system you're solving is where G is 100 or 80, and then S plus G is 200. So the second system is S is 120 and G is 80. So these are the vertices of the feasible region. And if I'm going to go back, step 4 is write the objective function. So here's where your information is. If the scientific calculator sold for a $2 loss and a graphing calculator is a $5 profit. So the cost is going to be, the scientific calculator is a $2 loss and the graphing calculator is I already forgot it, $5 profit. That's your objective function. So what I'm going to do in this line over here is I'm going to plug in my 200 for each scientific calculator, and I plug in 1 and 170 for G, and I'm going to write down what I get for my cost. So I plugged in each of these, 200 for S, then 170 for G, got an answer. Plugged in 100 for S, 170 for G, got an answer. So that was step 5. Plug in the vertices to determine which vertex maximizes or minimizes. So if I read right here, how many of each type should we make to maximize profits? We want to figure out which one of these vertices gave the highest answer. So that would be that we need to make 100 scientific calculators and 170 graphing to do the best for our company.